Yes, and welcome the senior fives for our geography lesson. Welcome, geographers, and good morning to you all that are tuned in to this lesson. Last week, we handled the second part of our topic of glaciation. And you remember when we were introducing ourselves to this topic, we, we said it was the remaining topic in regard to the exogenic processes that lead to landform formation in East Africa. Today, we want to introduce ourselves to another topic, a new topic, which is in the category of the internal processes, the ones that we refer to as the endogenic processes. And we said endogenic processes are those that originate from the interior of the earth. And this topic is the faulting. As you are well aware, that faulting is one of the major processes that have been responsible for the formation of landforms or relief features in East Africa. And actually, around East Africa, we have clear evidence that faulting has shaped the landscape of East Africa in terms of the various landforms that exist here in East Africa. And today we want to look at how this process has created landforms in East Africa. Like I said, that various processes have acted in East Africa to produce the current or existing landforms, among which we are saying it is faulting. And what is this faulting and how does it come about to result into landform formation? We shall begin with an understanding or a definition of what faulting is, because that is very important. We cannot start talking about the effect of faulting in terms of landform formation before we understand what it is and how it comes to occur in East Africa to result into landform formation. So faulting is the fracturing or the cracking of crustal rocks. And when we say crustal rocks, we are referring to rocks that make up the Earth's crust. You remember the structure of the Earth, where we said we have the upper layer, which is called the crust, and below it is the mantle. Then we have the inner part, which is called the core. So we are saying this faulting as a process of landform formation is the fracturing or cracking of crustal rocks and their displacement along the lines of weakness, along the fractures. So faulting as a process does not only stop at cracking of the rocks of the Earth's crust. It must continue and involve other actions. For example, we are saying there must be displacement of the rocks that have been cracked. When we talk of displacement, we are referring to change of position, movement of the blocks or the crushed rocks that have been subjected to cracking or the fracture. So when the rocks fracture or crack, then the forces that are responsible for the cracking or the fracturing must continue and therefore result or give rise to the displacement of the fractured rocks. And when we say displacement, we are referring to the rocks are either displaced horizontally or they are displaced vertically. So we're talking about lateral or horizontal displacement, or we are talking about vertical displacement. That the rocks get moved, but along the lines of fractures, along those fractures, which fractures are referred to as the faults. So we have fault lines or cracks within the acid crust that are created as a result of the faulting process, and that will result into the movement or the shifting, the displacement of the cracked rocks. And therefore, we shall have faulting as a process occurring. It is only after we have had the displacement that we shall have landforms developing. Because if rocks simply crack, then what shall we be talking about? We shall be talking about only the cracks existing within the crust. But when the rocks get displaced, then the structure, the shape, the appearance of the land surface is made to change, and therefore new structures will be created on the earth's surface. Therefore, that's when we shall say that faulting as a process of landform formation has occurred. So I want to repeat by saying faulting refers to the fracturing or cracking of crustal rocks and their displacement along the fractures or the lines of weakness that are created within the crust. Now, we are saying, or we have already said that faulting is an endogenic process. It is an internal process that takes place within the Earth's interior. Its origin is internal. Unlike other processes that we talked about, for example, we said we have weathering, for example. We talked about mass wasting. We have been talking about glaciation. Those operate on the surface of the earth. Those are exogenic processes. But faulting is an endogenic process because it has its origin from the interior of the earth. You will remember when we are talking about the formation of rocks, and more particularly the fire formed rocks, that is the igneous rocks. We did say that igneous rocks form as a result of solidification and crystallization of molten rock materials that come from the interior of the earth, that is the mantle. Still taking you back to the structure of the earth, we say on the top of the surface we have the crust. Below the crust we have a layer which is composed of molten rock materials known as the mantle. So within the mantle, rocks exist in a molten state. So in the same way, we are saying that faulting has its origin from the mantle. The forces that bring about the faulting process of landform formation originate from the Earth's mantle. That's the layer of molten rock materials which exists below the crust. See where we see fumes of fire coming out of the Earth's interior. Red hot materials from the Earth's interior. That's what we are calling the magma. So within the interior of the Earth, that is the mantle, we have molten rocks. And what happens there are two important processes that we must talk about. We talk about the geochemical reactions, the geophysical reactions, and radioactivity. If my physics still works, we say that within the interior of the earth, that is within the mantle, these molten rocks under great heat, because we said the rocks are made up of different minerals. So the rock minerals react amongst themselves, either chemically or physically. So we have both the physical and chemical reactions taking place within the Earth's mantle. And that's what we are terming as geochemical reactions. Rocks chemically reacting amongst themselves. Geophysical reactions, where rocks where rocks physically react amongst themselves. And when these reactions take place, then we shall have what we call radioactivity, radioactive decay, or the breakdown or the burning of the reacting minerals. So these three processes, that is geochemical, geophysical, reactive reactions, take place within the mantle. And when this happens, we shall have more heat generated because during these reactions, heat is produced. And when the heat is produced, the rocks exist in a molten state, and that results into what we are going to term as convectivity. Now, convectivity or convection, for that matter, we can talk of convection. Convection is the process by which heat is transmitted into liquids. So, when these rocks in a molten state uh, begin to get heated because of these processes, then they start flowing or moving. So as they flow, then that is what we are calling convection or convectivity. Now, the molten rocks, that is the magma within the mantle, begin to move by convection. So the molecules or the particles or the materials, the molten rock materials, begin to rise upwards towards the Earth's crust, at the base of the crust. So they move towards the crust, vertically upwards, and when they reach the bottom or the base of the crust, they flow horizontally and then back. Just like you boiling any liquid, say water or even porridge. The best is porridge because you can see the molecules. The molecules there are all particles of grains of the portion will be seen flowing within the saucepan. So the molecules rise, reach the surface, flow horizontally, then back, and then the process continues in that circular motion. So, in the same way, the molten rocks of the mantle are made to rise vertically upwards, reach the base of the crust, flow horizontally, and then back. So, that flow, that movement of the convective currents will produce forces, which forces may either pull or push the crust of rocks. So, if this is our crust, so below it we have the mantle. So, this is a section of the mantle, and then we have the core down here. So, we are talking about processes that take place within this section of the mantle. So, we're saying the currents rise vertically upwards on reaching the base of the crust, they flow horizontally and then back. So the process continues. So we have that movement of convective currents. Now, it so happens that as the currents move horizontally at the base of the crust rocks aboard on top of these currents will also be stretched, be pulled. So these forces, these currents will transform into forces that pull the crust apart. So in some sections, the forces or the currents are moving apart. And in other areas, we may have another zone where these currents may be moving towards this. So when you have a section where the currents are moving towards each other or where they are moving away from each other. So this zone here becomes a zone of tension. And this one here becomes a zone of compression. So in this situation, we are going to say that the convective currents move either divergently. So the currents are moving divergently, or in other zones, they may move convergently. And when the currents move divergently, meaning that they are moving in opposite directions away from each other, then we shall say that transforms into tensional forces. And when they move towards each other, we are talking about uh, compressional forces. Why? Because when the currents are pulling away from each other, then that means that the crustal rocks are also being pulled apart. When they are moving towards each other, it means that the crustal rocks are being pushed together. So that turns into compression, while divergent movement turns into tensional forces. So we're saying that uh, the tension and the compressional forces result into the strain and stress of the crustal rocks, which eventually results into their cracking. And when they crack or fracture, that results into the formation of lines of weakness, which we refer to as faults. So the faults will be created because of the tensional and the compressional forces. But in some cases, you may also have sections where the currents may move. So assuming these currents are moving below the surface, below the crust, but the currents are moving parallel to each other. They may move parallel to each other, but in the opposite directions. Not as in the case of tension, because tension, we said they are moving away from each other, but these ones are moving parallel to each other. So they are lateral or horizontal forces, but pulling in opposite directions. So when this happens, we shall also see that there is strain of the crustal rocks horizontally, and that results into tearing or still cracking, but by in form of tearing of the crustal rocks. And in this case, we shall be talking about this is what we shall call transform forces. So in this case, we are talking about the forces that are involved in the process of faulting are basically three: the tensional forces, due to the divergent movement of convective currents below the Earth's crust; the compressional forces, which are due to convergent movement uh, of the convective currents below the Earth's crust; and then the transform forces that move horizontally in opposite directions, parallel to each other, below the Earth's crust. And all these forces result into the fracturing or the cracking of the crustal rocks, and followed by their displacement along the faults or cracks, which gives rise to the creation of different landforms that exist here in East Africa, as we shall see. Now, um, so this therefore means that when we are talking about faulting and its origin, it brings us to those three forces, which forces will also give us three different forms of faulting. And these ones are what we call normal faulting, normal faulting is the fracturing, because we said faulting is fracturing. So normal faulting is the fracturing of the crustal rocks, which is caused by tensional forces. So normal faulting occurs as a result of tensional forces, and we see tensional forces are those that pull the crust apart. And therefore, the crust breaks or cracks as a result of being pulled apart. So we are saying this is the fracturing of crustal rocks caused by tensional forces that pull the Earth's crust in opposite directions, producing normal faults. So, if I may say, now if you are saying normal faulting is the cracking caused by tensional forces, then somebody may ask us, what is a normal fault? A normal fault is a fracture. A normal fault is a fracture or a crack within the Earth's crust or within the crustal rocks. is created or formed by still tensional forces. Here we are saying this is the process. Normal faulting is the fracturing. Now, a normal fault is a fracture within the crust, but produced by tensional forces that pull the crust apart. And we have evidences that in East Africa, when we compare the nature of the Rift Valley, the eastern arm and the western arm, we see that the eastern arm is more gently sloping. The sides of the Rift Valley are more gently sloping, and this shows us that along the eastern arm of the Rift Valley, we had the normal faulting there. That very formation of the Rift Valley, we shall see that. But we are saying the nature of the escarpments, those are the steep sides of the Rift Valley, that the nature of the escarpments along the eastern arm of the Rift Valley indicates that there was normal faulting. And so those caps there represent normal faults. For example, one called El Gayo fault. We have Mau and Rukwa escarpments. All these ones are found along the eastern arm of the valley. Elgeyo and Mau are found in Kenya, while Rukwa escarpment is found in Tanzania. When you get to the north, we have there an illustration of how a normal fault looks like. We are indicating the tensional forces, we are indicating the normal fault, and one slab is subsiding or sinking. When you look at that, you will understand what we're trying to demonstrate here. Then the other type is the reverse faulting. Now, reverse faulting is the opposite of normal faulting. Reverse faulting is the fracturing, because we are now describing a process, is the fracturing of crust or rocks caused or produced by compression forces. These ones said are caused by tension forces, but now these ones are produced by compression forces which push the crust or rocks towards each other. But because the tension forces pull apart, but here compression forces push towards each other. So we are saying this is the fracturing or cracking of crust or rocks caused by compression forces that push or press the Earth's crust towards each other. And this is because of, we said, converging convective currents that move towards each other. And this still, one may, now we are describing reverse faulting, but one may want us to, now what is a reverse fault? We have said in this case that a normal fault is a fracture caused by tensional forces. So similarly here, we are saying that a reverse fault is a fracture or a cracker within the crust of rock that is caused by compressional forces. And when in East Africa we want to have a picture of how how a reverse fault appears, right? We look at the areas along the Albertine Rift. When I say Albertine Rift, I mean the western arm of the Rift Valley around Lake Albert. That section there is what is referred to as the Albertine Rift, where we have a very steep escarpment called Butiaba Escarpment. So Butiaba Escarpment is an example of a reverse fault. I am emphasizing this because somebody may trick you that you have read and understood what faulting is, but somebody will only ask you a very simple thing. For example, what is the normal fault, or distinguish between a normal fault and a reverse fault, and then for you to start describing the process. So we are saying this is a fracture and this is also a fracture. So the Butiaba escarpment represents a reverse fault. We also have an illustration in this case which shows that very steep or inclined, a very steep inclined face of the rock. That is what we are calling a reverse fault, where one slab is uplifted in relation to the other because of compression forces that are pushing towards each other. So we are illustrating down there, the compression forces push together, and then one slab slides up to form. So that line of weakness that separates the two blocks is what we are calling a reverse fault. Then we said the third one, the third force in the other case was what we refer to as transform forces, where currents, convective currents move parallel to each other in opposite directions. So in this case, we are also going to have another type of faulting or form of faulting, which we shall refer to as tear faulting. So tear faulting is the cracking or fracturing, or you can use the word tearing. So it is the fracturing of crust or rocks caused by parallel convective currents that horizontally pull the Earth's crust in opposite directions. Like I demonstrated, that you have the forces moving, the convective currents are moving horizontally below the Earth's crust, because you say these currents first rise upwards, and then when they reach the base of the crust, they flow horizontally. So in this case, the currents are rising. When they reach the base of the crust, they move in opposite directions. So we have currents moving in opposite directions. So when they move in opposite directions, that means that they are also straining the crust in those opposite directions, and that may result into the tearing or cracking of the crust or rocks. So if I may, in simple way, illustrate tear faulting, that if you have the surface of the earth in this form, so our currents are rising below the crust. So that is the surface of the earth. So the currents are moving in the opposite directions. So these are what we termed as transform forces. They are moving in opposite directions. So this side, but we are now indicating this simply because we cannot now show this and below. So when this pulls in this direction, while the other pulls in the left direction and right direction. So what we shall have is that this block here, this land surface is being strained. And what happens is that the strain will cause a fracture within the crust. And then this will mean, therefore, that this block will move. So the blocks, into simple. So when the fracture develops, that means that this block has been divided into two sections. So this one will be dragged to the right, while this one is being dragged to the left because of the forces. So what we shall end up having are that this block moves parallel to, the blocks move parallel to each other. So the tear fault will be here. So this is what we are calling tear faulting. So tear faulting is also another form of faulting that will also help us to understand the formation of features in East Africa arising from the faulting process. And if you want to also justify, if justification for the occurrence of tear faulting in East Africa is the existence of fault-guided valleys. And fault-guided valleys, these are horizontal lines of weakness within the crust, and in many cases, these valleys have rivers flowing in them simply because when the land tears like this, so this area here becomes a valley or a line of weakness because of the displacement there, rocks are crushed. So when water flows in here, it can easily deepen this section to turn into a valley, which we are calling the valley. So Aswa in northern Uganda, and then we also have Ruaha in Tanzania. These are examples of areas where we can justifiably say we have tear faulting in East Africa. Now, having looked at this, that is what faulting is, how does it come about, or the forces involved, and then the forms or types of faulting, then we want to go to its effect on landform formation. There's not much that we need to know beyond that. That if this is what faulting is, and this is how it comes about, then how does it develop the landforms that we have in East Africa? So we are looking at the effect of faulting on landform development, or landform evolution, or landform formation in East Africa. I always want to use those words collectively. That is, we are talking about landform formation, you can call it landform evolution, or you call it landform development. We are meaning the same thing. How do landforms develop? How do landforms form? Or how do landforms evolve as a result of the faulting process? And this one here sometimes confuses people when somebody talks about landform development, and people think we are talking about human geography because we have used the word development. Somebody will think we are talking about the economic importance or the role of these landforms, the development. No, we are saying landform developing is landforms forming because they form by a process. So we're saying that faulting, as we mentioned right from the beginning, that faulting is a major process of landform formation, especially in regard to East Africa, because we have very clear evidences to prove that this process has been here and has led to formation of landforms here in East Africa. When we look around East Africa, we talk of landforms such as the Block Mountain. We have Block Mountains in East Africa. These are clearly known to have been formed as a result of faulting. We have our Rift Valley, the Great East African Rift Valley. It is a product of faulting. These two, in the first place, if somebody was told to give us the evidence of faulting in East Africa, and you don't mention these two first, then that will mean you don't fully understand this process of landform formation. So you say the Block Mountains, the Rift Valley, are one of the major and clear evidences that faulting has taken place in East Africa. Then we also have others like the grabens. These are the lakes that we have, those depressions with water, called now the lakes. They are called grabens in this context. Those grabens exist within the Rift Valley. There are several of them. That is also another clear evidence that faulting has taken place in East Africa. The other one is the escarpments, or the fault scarps. And of course, when we talk about the Rift Valley and the Block Mountains, we cannot fail to talk about the escarpments and all fault scarps, because the sides of the Rift Valley has got those steep slopes. The Block Mountains have got those steep slopes. Those are the ones that we are calling the escarpments or the fault scarps. Then we have the other one called the tilt block. The tilt blocks. So I'll be talking about this one. These are like ridges of hills, but with a series of hills with the depressions that separate them, or valleys that separate them. That landscape of that nature is called the tilt block. And then we also have, I've already talked about this one, the fault guided valley. Not river, we are not talking about drainage, but we are talking about landform. So we shall call that one fault guided valley. So in simple terms, these are the evidences in terms of landforms that show that faulting has occurred in East Africa. And our duty is to explain, to have an understanding of how these different landforms were formed in East Africa by the process of faulting. Another thing, we shall quickly go through these landforms, and I will refer to the notes that are displayed on your screens. You have time and read through them. And are well aware that when we are talking about geomorphology in Geography Paper 1, we are talking about knowledge. So I have kept on telling you that in physical geography, we are looking at knowledge, depth of understanding of a concept. So we are here to demonstrate our knowledge of the process of faulting in regard to landform formation in East Africa. And we said ours is to identify a landform, describe it, then explain how it forms. You explain the formation, that is when you bring in the processes, but of course here we're talking about one process, that is faulting. Then we shall give examples and then give an illustration. And I always prefer telling you we need a sensible illustration. If you must illustrate, then illustrate sensibly. Don't just draw for the sake of drawing. What you draw must be in line with what you have described and how the explanation has been. So we are saying, do we know that faulting has taken place in East Africa? Yes. How? Because we are able to tell that there is a block mountain. We have identified. We describe what a block mountain is. We explain how it forms. We give examples in East Africa, and we also illustrate them grammatically. And that's what we have done in the notes that are displayed on your screen. I will encourage you to read through and understand the topic of faulting, because it's one of the simplest and interesting topics as regards geomorphology in East Africa here. So, to begin with, we are saying that faulting has led to the formation of the block mountain. Of course, we all know that a mountain is an upland. Simple. But how can we describe a block mountain different from a volcanic mountain? So we're saying we have identified the block mountain as a landform formed by faulting, and then we are describing it as an upland which is bordered by fault scarps. So fault scarps are those steep slopes that are created by faulting. So we're saying this is an upland bordered by fault scarps on either sides. So the sides of the mountain of this upland have got steep slopes called fault scarps. So we are saying it's an upland which is bordered by fault scarps on either sides and stands above the surrounding as a host. That's why sometimes we say the block mountain is also known as a host. So it is that upland with the fault scarps on either sides, and it is a host. It is an outstanding part of land around the surrounding. That's why we refer to it as a host. The block mountain is formed either by compression or tensional forces. We shall see at some other stage when we go into the details of block mountains, because this can be another subtopic of this topic when we look at particular essential or significant landforms resulting from faulting. So, the block mountain, we are saying, is either due to tensional or compressional forces. So that means, therefore, that we can explain the formation of block mountain using compressional forces or using tensional forces. But we shall also see we can still explain its formation using other mechanisms, but all under faulting. So what's important here is not talking about that it is formed by faulting. That's what we know, because we are talking about landforms that are formed as a result of faulting. But what we are saying here is that the faulting is either that which is caused by compressional forces or that which is brought about by tensional forces. So the best, because we are talking about knowledge. We are explaining, we are showing knowledge of the formation of the block mountain. If we are looking at all landforms generally here, it would be nice for us to use the two versions that explain, because there are others, but we don't have now to exhaust all of them at this stage. That means that we shall be overemphasizing one landform, yet there are several others to be talked about in regard to those that result from faulting as a process of landform formation. So we are saying it is formed either by compressional or tensional forces. So we explain how does a block mountain come into existence as a result of compressional forces, because that is what is most convincing. So we begin with that one. So compressional forces must have pushed, or we could begin from convergent convective currents. So these convergent convective currents must have produced compressional forces, must have generated compressional forces within the Earth's mantle. We said these compressional forces are those that move towards each other. So convergent convective currents within the Earth's mantle generated compressional forces according to this explanation or theory. You can call it a theory. A theory explains the formation of the block mountain. So we can call it the compressional forces theory for the formation of the block mountain. So that these forces which were converging, or currents that were converging below the Earth's crust, must have produced compressional forces that pushed and stressed the Earth's crust, leading to the formation of, or leading to the occurrence of reverse faulting. So there was reverse faulting due to compressional forces and the formation of reverse faults. So convergent currents, convergent convective currents produce compressional forces which push and stress the crust or the crustal rocks, leading to reverse faulting and the formation of reverse faults. But remember, we said that faulting is incomplete until there is displacement of the faulted or cracked rocks, or fractured rocks for that matter. Then, so we are saying that as a result of this, the forces of compression that we are pushing together did not stop. So continued compression forces, continued pushing or further pushing of the crust, which have been already subjected to reverse faulting, resulted into the uplifting of the block of land. So if this is the land, that's the crust. These are simply layers or horizons of the crust. Where this is the crust. Now in the mantle here, that's where we are talking about the currents. So at the base of the crust, we have the currents, and then we shall have the reverse faults created because of this. So compression forces here must have pushed, and therefore resulting into the cracking of the crustal rocks to form these that we are calling the reverse faults. So when the forces continued pushing, then the block of land here between these reverse faults was forced to rise. So this is what we end up having. So there is uplifting of the block of land between the reverse faults, and this area here remains standing above the surrounding as a host, or this is our block mountain that we're talking about in this case. So here, these compression forces continue, the middle block therefore is uplifted. We have that illustration clearly there. Then we are also saying that the explanation for the formation of the block mountain is not sufficient if we only use one theory or one explanation. So the other version of explanation will be in relation to tensional forces. So how do tensional forces bring the formation of a block mountain? So for compression forces, we say converging convective currents. So in this case, we have diverging convective currents, diverging convective currents pull the crust apart, and when they do so, they transform into tensional forces. These tensional forces then pull the crust apart, leading to normal faulting. And when normal faulting takes place, then what is created are the normal faults. So after the formation of the normal faults, we continue. The forces that are pulling do not stop there. The currents continue rising and they move divergently below the crust, therefore pulling the crust further apart. And when this happens, after the normal faulting has occurred and the creation of the normal faults, then further compression, further tension of forces will result into the sinking of blocks on either sides of the normal fault. So this is what we have, and then the forces in this case are pulling apart. So this is tension forces. So these tension forces pull apart the crust, and therefore we shall have the normal faults created. So these are what we are calling the normal faults. And when this continues, the pulling continues. So further continued tension of forces will result into, we said, it is the side blocks. The side blocks are made to sink or subside. I want to make it quick, a simple one like this. Is clear on the notes, you'll see. So in this case, we are saying as the forces continue pulling, the blocks on either sides, on the sides of the normal faults, will sink. So this block here sinks, and there are also some sides of sinks, where the middle block is left standing above the surrounding as a block mountain. Of course, for us here, we explained how the block mountain could have come into existence. Don't ask me whether, now what about here? We have these angles here. Are they hanging in that form when you go around the block mountains? The answer is no. These areas must have been subjected to erosion and mass wasting. Therefore, you have still steep but not as inclined and vertical as this. So, we are saying the block mountain is either a product of compression forces or tensional forces. And having explained the block mountain fully, using tension and compression forces, we can now able say these mountains that we have in East Africa, which are block mountains, may include Mountain Rwenzori, Mountain Usambara in Tanzania. Of course, there are not very many, like volcanic. Then we have others like Ufipa, that is Tanzania. We have others like Matthews Ranges, which is in Kenya, and etc. etc. Then the other landforms, we said there are two major landforms that one must first explain if we are looking at landforms resulting from faulting in East Africa. So having explained the Rift Valley, the Block Mountain, the other one is the Rift Valley. If we explain these two fully today, we shall have done a great deal of our journey in the understanding of the effect of faulting on landform formation in East Africa, because these are the major landforms that we have. Now, the Rift Valley, like we did for the Block Mountain, we are following this pattern. So we are saying that what is the Rift Valley in the first place? If we agree that it is one of the landforms resulting from faulting in East Africa, the Rift Valley is an elongated depression on the Earth's surface, which is bordered by in-facing fault scarps on either sides. Implying that we are talking about a depression which is long. I don't want to use the word narrow, because when you say narrow, some people think we are talking about just something like a trench. It is an extensive area, so it is simply an elongated depression on the Earth's surface that is bordered by in-facing fault scarps. That the scarps are facing each other, or are facing the inside of the valley of that depression. So that's what we are calling. That's what we are calling fault scarps. That's what is known as the Rift Valley. Now, like our Block Mountain, the Rift Valley can also be explained using various theories. So here we even have more theories, about 5 of them, that explains the formation of the Rift Valley. But at this stage, we want to use only 2, exactly as we have used 2 in explaining the formation of the Block Mountain. And still, the theories shall remain these 2. That is, the theory by compressional forces or the tensional forces theory. So these are merely 2 explanations that we want to use at this stage. And the others we shall look at when we go into the details of how the Rift Valley of East Africa was formed. Now, in East Africa, we know that the Rift Valley, we don't even need to waste the time saying we are going to give the examples at the end. But we know that in East Africa, the Rift Valley is one of the most outstanding landforms resulting from faulting, because we have it running from northern Kenya around Lake Turkana. It runs southwards up to, it crosses into Tanzania up to Lake Nyasa or Lake Malawi in the southwestern part of Tanzania. Then from that point, it divides. Then it creates another branch that runs northwards, but along the western side of East Africa. That is, it runs along Tanzanian border to the west, and then goes up to Lake Albert, northern shores of Lake Albert. That is in Uganda. So that is the western arm. So we are saying this Rift Valley could have been formed by tensional forces. Tensional forces, which tensional forces are caused by divergent convective currents. So the divergent convective currents must have operated below the Earth's crust that was in the mantle, and this resulted into tensional forces that pulled the Earth's crust apart. And as a result of the pulling of the crust of rocks, there was no more faulting. So no more faulting occurred. And as a result of no more faulting, there was creation of no more faults. So the no more faults were created because of no more faulting within the crust, because of tensional forces, which have been brought about by divergent convective currents. And when the forces of tension continue, so if this is, so we have already seen that the normal faults appear in this form. Those are normal faults. So our normal faults are created because of tensional forces. So tensional forces pulling the crust apart, normal faults created. And as the forces continue pulling after the normal faulting, Then the structure of the landscape was left like this. So, in this case, we are showing that because of uh, the tensional forces, in this case, I want to emphasize this, in this case, the middle block, the block of land, the block of the crust, which is between the normal faults, sinks. So, this middle block was meant to sink while the side blocks remained stable. Because they had been moved apart, so the middle block remained uh, unsupported. So, therefore, it sank under its own weight or subsided. So, meaning that we have that depression created on the Earth's surface with the scarps. So, these are what we are calling the infesting fault scarps. So, these are fault scarps on either sides. So, this is our valley in this case. We have that illustration in the notes. Refer to it when you are reading about this. That is according to tensional forces. Then we are saying the other version or other theory or explanation is the compressional forces theory. The compressional forces also explain the formation of the Rift Valley, and they said compressional forces are brought about by converging convective currents. So the converging convective currents operating within the Earth's mantle or below the crust resulted into compressional forces. The compressional forces led to reverse faulting and the creation of reverse faults within the crust. Faults are cracks within the crust. And then when the forces continue, so this is what we are showing at this stage. So we have, that is the crust, and so we have forces of compression pushing towards each other, and then the cracks are of this shape. So these are reverse faults. Now, when the forces continue pushing, this is what we have. So we shall end up having something of this kind. Something of this nature. So in this case, the blocks on either sides, the blocks on either sides of the reverse faults are the ones that rose because of compression forces, further compression forces. So the blocks on the sides rose in this form, therefore leaving the middle block stable and below, therefore creating a depression on the Earth's surface with a very steep in-facing fault scarps. So here these scarps here are more open or gentle. Here these ones are closed or inclined, more inclined and very steep. Because other processes may have come into existence. For example, they came into operation. For example, mass wasting and erosion, therefore reducing these sharp angles of the fault scarps that were created in this form. And this one, remember we said the Rift Valley along the eastern arm is more gently sloping. The scarps are more gently sloping, representing normal faults, while around the Albertine Rift, that is the section of the Rift Valley around Lake Albert, has very steep scarps, which represent reverse faults. So, to justify this theory, we refer to the Albertine Rift, and to justify this theory, we refer to the eastern arm of the East African Rift Valley, especially around or along Kenya. So, these two theories also explain for us the formation of the Rift Valley, just like they did for the formation of the Block Mountain. But one thing that we need to be very careful with is, in this case, we are showing that under normal faulting, the middle block sinks. That is the Rift Valley. While under compression forces, the side blocks rise. But you also remember that when we are talking about the block mountain, we said when there is compression to form a block mountain, then the middle block rises while the side blocks remain stable. And we said what is the rift the block mountain formation in relation to tensional forces, the side blocks sink while the middle block remains stable and up or above the other side blocks to form a block mountain. So be careful not to interchange these illustrations when it comes to formation of the block mountain or the Rift Valley by the two major forces, that is tensional and compressional forces. I want to suggest that and thank you, because in the interest of time, our lesson stops at this, and I want to thank you for attending, and we shall add on from here because this is just the our topic of faulting. Have a good day.